Alright, hey guys, welcome to part 3 of Boolean Algebra. Let's just quickly finish this off. So, the main topic will be parity and circuits, well, the construction of the series or the schematics. Well, what is parity? Well, parity is true or 1 when you have an odd number of 1 inputs. That's probably the most important part. And the other one, obviously, if parity is false or 0. Parity is false or 0 when you have an even number of inputs. Now, just to display this, if you have 0 ones, that's even number, so your parity is 0. You only have one in this row, so that's an odd number, hence your parity is true. 2 ones, parity is false. 3 ones, parity is true. Well, what's the point of parity? Well, parity can help you with schematics, as we'll see later on today, and it can also tell you when you have transmission errors. How? Well, let's say you were expecting to get 1, but you got 0, this guy. Well, you know something went wrong in transmission, and hence parity can give you a solid understanding. But then again, one thing to realize is, let's say you have a combination of 1, 0, 1. Your parity in this case, it's even, so it'll be 0. Well, let's say it changes to 0, 1, 1. Your parity is still 0, so you will never know if you made a mistake. So parity isn't foolproof, but it does provide you with a solid understanding, or maybe potentially tell you that there's a transmission error. Next, we'll be going over the 3 input gates. Some of them, the important ones are the selection, rejection, multiplexer, and the majority gate. Selection and rejection, it's very self-explanatory, where selection only allows, you select the one you want to get through, and you only reject the one you want to get through. In this case, it's an acceptance one or a selection one. And if you forgot your schematics, the little legend over here, the popsicle looking thing is the and the circle means not. So this branch over here, it's saying A with a circle, so it's A naught. B is just a line, B, and C, there's a circle, so it's C naught. And because of this popsicle like thingy, you know the equation is A naught, B, and C naught will get you X, which corresponds to these truth and false values. The multiplexer looks like a weird trapezoid. And all it states is, like in 2001, if you remember, if you don't, if C is 0, C is an input, B will get through to F. But if C is equal to 1, A will get through to F. And the actual gate in schematics looks a bit different, but you can just show it like this. And thank the Lord for that, because the next one is a hassle. This is called the majority gate. And all it states, if you have 3 inputs, or no, depending on your inputs, if the majority of the inputs are 1, then you will get M. So in this case, if A, B, and C, if 2 out of 3 of them have a value of 1, they'll get through, dictated by this. And since it's a majority gate, and we don't have to draw it, we can draw it like this, and that's super awesome, because this is the equation, and it's really ugly to draw out because you obviously need 3 ands minimum, and you need 2 ors, and that's annoying to draw, but thankfully we can just show it like this. Alright, next on, we're gonna just do a quick review in binary addition. All you have to remember is 1 plus 1 gives you 0 carry 1 in the next column. And this is the 2 to the 0 column or place, and this to the 1 place. Now, 1 plus 0 is 1. I'm doing this one. 1 plus 1 is 0, carry 1. And that gives that. And this one is just 1 plus 1 is 0, carry 1. And then you have 0 plus 1, which is 1. And you have 1, carry 1. And these are your corresponding decimal values. And this comes into play in the next 2 notes. This is actually taken directly from his slides. It may look a bit confusing, but we're going to get through this. So, here are your inputs. You have your A, B, and C input. And your outputs are sum and cy. Now, cy is actually the 2 to the 1 column, and the sum is 2 to the 0 column. And I'll show you what I mean by that. We're going to say it's 2 to the 1, it's 2 to the 0. Alright, so let's look at this line. Alright, so your A is 0, B is 0, and your cy, or cyn, is 0, 1. If you add them all together, you get 1, 0. This is a bit off center. So since the sum column is 2 to the 0, and this is 2 to the 0 place, it becomes 1, and it is. And your cy is this column, which is 2 to the 1, and that's why cy is 0. Now, you can do the same thing for this line and this line, and you'll see the corresponding digits that go in here and here are based off of your addition. So that's why we ran over binary addition. Now, the next thing to do is to get these equations, and the way you get it, all you do is you look for when the sum is 1 or sigma is 1, and when cy out is 1. He already has arrows drawn out, so that kind of helps me, but here are all your 1 values. I missed that one. So you had this one. How'd you get that? Alright, well, all you do is you look in the row. Since these are the values, A0 must be 0, B0 must be 0, and C0 must be 0. Since we have A and B equals 0, you know it's A0 and B0, and cy is 1, you know that just stays like that. And they're being added together because A with input of B, A of 0 with input of B of 0, and C with input of 1 gives you this value, so you know they're being added together. And you go ahead and do that for every other 1 value, or the true value for sum. And the exact same thing for the cy. Well, what's so important about the sum column? Well, it's actually the same thing as parity if you work it out, as you can see by these two columns. What? Yeah. So the reason you get the equations is to draw the schematic. But there's another easy way of doing it, and that's with parity. So parity, again, if you remember, is false when there's an even number of ones, or p is 0 with even number of ones, and the opposite holds true as well. So we really care about when parity is true, so these guys. But how do you get that? Well, let's look at the combinations. Let's look at this one right here. If 0, 0, 1 gives you true, are they being ANDed or XORed or a combination? That's what we have to ask. Well, let's start with AND. You know all of them can't be ANDed because as soon as there's 1, 0, the whole thing is false. Can all of them be ORed? Yeah, because OR requires one true value. Sweet. But now you have to test it for the other ones as well. Well, hold on. Why is this one false? 1, 0, 1. If they're being ORed together, there's 1, so it should be true. But it's false. Damn. Whoa, wait. Isn't there one of them that if there's only one, it's true? Yeah, and that one's XOR. And you'll find out that XOR works for all of them. Even this one right over here, you're saying, wait, there's 3 ones. XOR requires only 1. How can it be true? Well, this was the one that indicates that they're being XORed sequentially. Because 1 XOR 1 will give you 0. XORed with 1 will give you 1. And yeah, that's how they find out these are the XOR gates. Since you know it's sequentially, A and B are being XORed, and the outcome of that is being XORed with cy. Truthfully, it could have been like this as well. Oh god, just pretend that's a XOR one. And we gotta draw that again, goddamn. I'm gonna pretend that's that. It could have been like this as well, but you know, doesn't really matter. But thanks for tuning in for Boolean Algebra Part 3 of 3. Hope to see you guys next week.